So good afternoon. Today I'm going to talk to you about multivariate regression modeling and inferential frameworks for brain network analysis, and specifically exponential random graph models and mixed models. And so here's an outline for my discussion. First, I'll talk about the impetus for the development of these multivariate regression approaches. I'll then briefly touch on brain network construction and description. And then I'll get into these multivariate regression modeling and inferential frameworks. And these will be discussions about their implementation for static brain networks. And there still remains work to be done on adapting them to the dynamic network context and the multitask network context, although I'm becoming increasingly skeptical about whether or not it's worth the time to adapt them to the dynamic network context after Steve's talk. I'll then kind of end with a summary discussion of the pros and cons of both of these approaches, and then leave you with some useful resources. And so, as we all know, connectivity and network analyses have exploded over the last decade or so, maybe about 12 or 13 years, because of their potential in helping us to understand both normal and abnormal brain function. Now, connectivity analysis examines associations between time series and specific brain regions, whereas I think of network analysis as a distinct subfield of connectivity analysis that quantifies the association between time series in all regions to create an interconnected representation of the brain, or brain network. And the appeal of this network approach is that it allows us to examine how systemic properties of the brain relate to behavioral and health outcomes. And while connectivity analyses underlie network analyses, the subtle distinction between what I consider two interrelated domains is often overlooked in the literature. So it's our systemic organization of our brains that confers our functional capabilities, as connections may be lost due to some adverse health condition, but compensatory connections may develop to maintain organizational consistency and functional performance. And so here we have a graphic illustration of that. So you may have two individuals or two groups of individuals that have a network disconnection between two regions, but the brain may compensate for that and develop an indirect path between those two regions, or a previously silent path between those two regions. So two individuals or even two groups of subjects may exhibit differences in connectivity while exhibiting no differences in network structure. Also, connectivity analysis focuses on direct connections between regions, but network analysis allows us to examine indirect connections between regions as well, and hence the need for sort of multivariate approaches that allow assessing the entire network simultaneously. So here's just a schematic for how we generate our network from fMRI time series. Most of you are familiar with this, so I won't belabor this slide, but basically we get our bold signal values over time from the various regions of the brain, depending on our parcellation scheme. And then we look for functional associations between all pairs of time series to give us our connection matrix. And as you've heard in previous talks, there are a number of ways to get this connection matrix. And then often people will threshold this connection matrix either to remove negative connections if you're using correlation, and or to remove sort of weak or quote unquote non-significant connections. And then you're left with your network, which is our unit of analysis. So this is sort of what I'll focus on when we're interested in sort of modeling networks and comparing networks across individuals in groups. And so this work is somewhat independent of how you actually create your network to begin with. And so once you have your network, the next step is to describe your network. And so we're all pretty familiar with the small world metrics. Those are sort of the most commonly used metrics to actually describe the systemic properties of your network, where clustering coefficient can be thought of as a measure of the local communication ability of your network or its regional specificity. And path length can be thought of as the global communication properties of your network, or its ability to distribute processing. We often look at degree, which is just the number of connections of each node, or the sum of the weights of the connections of the nodes in the weighted network case. And we generally assess the distribution to assess the network type or resilience properties. So for instance, assortative networks where you have high degree nodes connected to high degree nodes and low degree nodes to low degree nodes tend to be resilient to random attack, but very vulnerable to targeted attack. Now, graph centrality and information flow metrics quantify the relative importance of a given brain area for the transmission of information in a network. And there are many metrics out there. We tend to use leverage centrality, which identifies brain regions that have a high degree relative to their neighbor. So basically, they're heavily influential over their neighbors, but not heavily influenced by any one neighbor. And then as Danny described, we also tend to look at community structure, where we look at how well the network sort of subdivides into interconnected communities for an efficient division of labor. And so this is just sort of an illustration of that in the static network case, and Danny touched on approaches for the dynamic network case. And so in order to try to systematically analyze all of these systemic properties of networks, we really need a multivariate, explanatory, and predictive brain network modeling approach. And so if we want to denote the network of subject I by Y sub I, so you can sort of think of this as the adjacency matrix for subject I, and the covariate information of subject I by X sub I. And so you can think of this as both endogenous covariates, so things that are inherent to the given network, and exogenous covariates, things that are phenotypic properties of the subjects, like gender, race, health status, etc. We want to be able to relate the network of subject I to their phenotype, basically. So we want to be able to model the probability of a network given these covariates for an individual. So in pictorial form, we just want to be able to relate our network to both the sort of local substructural properties of the network metrics and our covariates of interest, where the theta parameters sort of relate the phenotype to the network structure. And so one such approach for doing that is using exponential random graph models, or an ERGM framework. And so you don't have to worry too much about the math here, but basically what we're doing is you'd be modeling the probability of seeing a network given sort of local substructural properties of that network. So the G of Y capture properties of the network, things like clustering and path length and leverage centrality. And then the theta parameters relate those properties to the overall network structure. So they tell you how important those specific systemic properties are in describing the overall network structure. And so the goal of these models is to identify the local metrics that sort of concisely summarize the whole brain network structure. And once you have these sort of most appropriate network statistics, you could then use parameter profiles to classify and compare whole brain networks. So for instance, if you have 10 normal subjects and 10 subjects with a specific health condition, you could fit 20 models, because you actually have to fit these to each individual network. So you would fit 20 of these models, and let's say for all of them, the best model consisted of the number of edges in the network, the clustering coefficient, and the path length. You could then use these theta parameters, theta 1, theta 2, and theta 3, to do formal statistical comparisons of differences between groups of brain networks and between individual networks. There are a couple of caveats, however. One is that comparisons require the use of a uniform set of predictors. In other words, you have to have the same best model for all of your subjects. So all 20 subjects, you have to fit this same model in order to do formal statistical comparisons. Now, you could do informal comparisons. If you were to get different best models for various groups, you could informally infer that there are some differences there and probably examine what those differences are, but you couldn't do any formal hypothesis testing with different network metrics. You also need balanced networks, in other words, the same number of nodes for each network, but we tend to have that by construction in our networks. Now, in order to select the best set of explanatory network metrics, it's best to use the graphical goodness of fit approach, that was put out by Hunter. And this graphic here sort of gives you an intuitive feel for how the graphical goodness of fit approach works. So first you select your model, you select your covariates to go in your model. You then fit that to the observed network, and thus you get estimates for your theta parameters. And you now have a fitted ERGM model, or a fitted probability mass function for your network. And then you can randomly generate networks from this probability mass function. And so the question then becomes, how does your observed network look as a representative of these simulated networks? And if the model does a good job of fitting the network, it should look fairly representative. And so as a proof of concept, we fitted ERGMs to networks from 10 normal subjects. And there are several R packages available to fit these ERGM models. The one used here was just the base ERGM, which is probably the one that you would use, but there are several others. There are a couple for weighted networks, although they haven't been employed in the brain network context yet. And there's one for temporal networks, but that hasn't been employed in the brain network context either. And the main point of distinction is that a lot of these have been developed for social networks, and so they just fitted to one network at a time, whereas in the brain network context, you have to adapt these to the multi-network context, which can be a bit of a challenge. And so what we found in our proof of concept work is that the final models for each subject provided a good fit to the data, as evidenced by the goodness of fit plots. So here we have an example set of goodness of fit plots for one of the subjects. On the x-axis, we have various network metrics. This is analogous to path length. This is analogous to clustering. We have degree, and then we have another systemic property called triad census. And basically the y-axis more or less gives the probability of seeing a pair of nodes or a dyad with that given network value. And the solid line represents the observed network, the distribution for the observed network, and the box plots represent the distributions for the simulated networks. And so we could see that our observed network looks very representative of the simulated networks. And so we can conclude that these models are providing a good fit to our brain network data. So here's just an example of that observed network and one of the simulated networks from the fit. Now we can also use this sort of ERGM-based framework to create group-based representative networks via simulation. So basically what you would do is if you have 10, let's say, normal subjects, and you want to create a representative brain network that represents these normal subjects, you could fit 10 models, one to each network. You would then average those theta parameter estimates, and so then you would use that average as sort of an averaged ERGM model. And then you could simulate representative networks from that average ERGM model, which actually provides a much more principled way of creating the networks than what's been traditionally done, which is to, let's say, take the 10 connection matrices or the 10 adjacency matrices from the subjects, and then people tend to either take the mean of those and then threshold the resulting matrix, or take the median of those and then threshold the resulting matrix. And they use that resulting matrix as their group-based representative network. However, it can be shown that network is actually not very representative topologically of the subjects it's supposed to represent. But this ERGM-based approach allows you to both sort of capture the average topological properties of the group and the distributions of those properties. So here we have a figure that sort of illustrates that, where we have distributions for 10 subjects in the green for path length, clustering, local efficiency, and global efficiency. And the group-based representative network that you get if you take the mean or median of the connection matrices is given by the blue and red lines with the circles. And we can see that it's fairly far off in some of these cases. But the representative networks that you get from the ERGM-based approach actually represent the distributions of these topological properties very well in the subjects that they're intending to represent. So the advantages of the ERGM sort of framework are that it provides a principled approach to topologically modeling, analyzing, and simulating complex brain networks. And its greatest appeal lies in its ability to sort of efficiently represent very complex network data as a function of just a few substructural properties. However, it's not well suited for local examinations, so it's not well suited for edge level examinations. It's better suited to look for systemic differences in networks. Multiple subject comparisons can pose problems because, again, you have to have the same best network for each subject. And there can be some difficulty in incorporating novel metrics, perhaps more rooted in the biology, due to degeneracy issues that these models can have. And most of its development has been for static brain networks. The development for longitudinal and weighted networks sort of remains in its infancy. So the sort of two-part mixed modeling approach actually provides a complementary approach to address some of these limitations of the ERGM models. And so in this two-part mixed modeling approach, we're basically modeling the probability of a connection as a function of network metrics and covariates, and the strength of a connection if it exists as a function of network metrics and covariates. And so just briefly in statistical notation, we're using a logistic mixed model to model the probability of a connection as a function of network metrics, some covariate of interest, confounding variables, and interactions. And I think this is important because often in the literature, people do comparisons without controlling for confounding variables, which can lead to a lot of erroneous results. So I think it's important that we have sort of this multivariate regression framework to be able to account for confounders. And then we also model the strength in a similar fashion. Here, this is just using a Fisher-Z transformation if you happen to be using correlations, but you can use any network generation approach and apply this model to that. And then the theta parameters are aiming to try to capture some of the variability in the network data. And so those theta parameters just consist of a parameter that sort of captures the deviation of an individual subject's sort of intercept. And so the intercept can be thought of as the proportion of edges for the binary case and the sum of the weight of the edges in the weighted case. So this is sort of capturing how much each individual deviates from the sort of group mean. And then we also look at deviations of individuals from the group mean in terms of the metric edge relationships. So what's the relationship if you have two nodes with high clustering, what's the probability of being connected? There's a certain relationship there, and this captures how each individual's relationship differs from that average relationship. We also look at the deviation of subject-specific spatial distance edge relationships. So the relationship between the spatial distance of two brain regions and the probability and strength of that connection. And then we like to account for whatever's left over, the propensity for each of the brain regions of a given dyad to be connected and the magnitude of that connection. So we're sort of looking at the latent relationships. And so this two-part mixed modeling framework allows sort of explaining or quantifying the relationship between network metrics, some covariate of interest, and confounding variables, and the probability and strength of connections in your network. It allows formally comparing connectivity, network structure, and edge properties by some covariate of interest, so for instance between groups, but you can also look at differences by continuous phenotype too. It allows predicting connectivity and topology based on participant characteristics and network structure and its variability via simulations. It allows leveraging group-level data to better distinguish between true weak connections and noise in individual-level networks. So here we're fitting one model to all of the networks simultaneously, unlike with ERGMs where you have to fit the model to each individual network. And it allows simulating group and individual-level networks, which can be useful for model goodness of fit assessments, representative network creation, and network variability assessment. So just to illustrate the implementation of this model, one study we examined was a study called the Aging Brain, where we were looking at the effects of aging on the integration of sensory information. And so we had two groups, younger adults and older adults, and they were scanned under three separate conditions: at rest, during a visual task, and during a multisensory task. And here we use 90 node AAL atlas-based networks for each participant. And so here for the network metrics, we had the average clustering of 2 nodes, the average global efficiency of all pairs of nodes, the degree difference between pairs of nodes, and the average leverage centrality between all pairs of nodes, and then the overall modularity of the network. Our covariate of interest was age group in this case, and we controlled for sex, education, and spatial distance squared, since there was a nonlinear relationship between distance and connections. And then we looked at the interaction of that covariate of interest with the network metrics. And so just to illustrate one of the modeling approach's utilities, we looked at the prediction intervals for connection probability as a function of degree difference in young and older adults. And so what we can see is that in older adults, when you have 2 regions with the same degree, that they have a higher predicted probability of being connected. But this decays at a faster rate than for younger adults as the difference in degree becomes greater. So in other words, older adults have more degree assortative networks at rest. Contrastingly, younger adults have more degree assortative networks during a visual and during a multisensory task. And so this is sort of in line with the hypothesis that older adults tend to be more distractible or cognitively vulnerable while engaged in a task. And here we have prediction intervals for connection strength as a function of degree difference. And so what we can see is that older adults tend to have a slightly lower predicted strength between 2 brain regions with the same degree. And the decay parallels that of the younger adults as the degree difference becomes greater. And this is the same during a visual and during a multisensory task. So in other words, older adults tend to have weaker coupling between brain regions regardless of the regional connectivity structure. So in another example, we implemented this model in a study that was aiming to examine the impacts of pesticide and nicotine exposures on farm workers' functional brain networks. And so what the model produced after controlling for many of the confounding variables in this study is that farm workers still tended to have a very different network that was more modularly organized with higher functional specificity and lower intermodular integrity at rest. And so this sort of modular structure at rest has been linked to sort of detrimental consequences. While it's good to have this while engaged in a task, it's not necessarily good to have this structure at rest. And so currently we're developing a MATLAB GUI interface to implement this 2-part mixed modeling approach. This is just a very preliminary version. It will have Python, R, and SAS sort of running in the background, but it will allow you to start from your time series, choose your covariates, choose your network generation approach. We'll be adding, of course, to this full and partial correlation. It'll allow you to choose your network features and so on. And so in comparing these 2 approaches, they sort of provide complementary multivariate approaches for analyzing data at the network level. In other words, for assessing systemic infrastructural properties of networks as opposed to just properties of specific nodes or connections. ERGMs allow efficiently representing network data with just a few local substructural properties. However, it's not well suited for edge-level examinations comparing groups or assessing network phenotype relationships. Mixed models are well suited for these examining specific connections, group comparisons, network phenotype relationships. However, it can be somewhat limited in its ability to capture the inherent topological structure of networks. But our work has looked to sort of adapt these models to that context and attempt to capture some of that topological structure. And they can be thought of actually as sort of a rudimentary connectivity network hybrid because they allow you to look at individual edges and systemic properties of the network. And they may provide the machinery necessary to develop more advanced sort of hybrid connectivity network methods. But they'll at least be beneficial in joint network connectivity analyses in conjunction with an appropriate connectivity method, sort of akin to maybe multimodal imaging. So I'd like to acknowledge some of my collaborators on this work, the funding institution, and others that have contributed to this work. And I'll leave you with some useful resources for implementing these 2 approaches in the brain network context.